Let us now look at the Stock and Watson common trend representation. To arrive at this representation, we start from the second equation in Phillips triangular representation. And we will now use the same partition into our lag polynomial psi L that operates on our error terms. So we have the series in differences partitioned into a subvector of dimension h and one of dimension n minus h. That is then equal to the partitioned lag polynomial applied to our error process. Or in other words, the lag polynomial psi L has these two subparts over here. So in essence, an alternative way to rewrite this second equation of Phillips triangular representation is working directly with this subpolynomial JL. From here on, let us continue by plugging in the Beveridge-Nelson decomposition for this guy. And I'm not interested in the exact form of the new error term, so I just compactly define it through a new name, namely the difference of eta t. And in the last step, I again sum over all time points s equal from 1 up until small t, like I did in the first video, to arrive at this expression for this series in levels of the second subvector, namely y2t. Then I'm almost there, and this already forms the second set of equations for the Stock and Watson representation. To get the first equation, I just need to plug in this expression for y2t that I just derived into the first equation of Phillips triangular representation. So plug this guy into this, and then when you combine everything, I indeed arrive at the so-called Stock and Watson common trend representation. Now, let us also pause here and have a closer look at this co-integration representation. I've recopied here on the next slide. First, notice that I now have all the series in levels that pop up at the left-hand side of the equation. So this is already different from Phillips triangular representation. Now, each of these non-stationary series is split up in 3 parts. We have some initial conditions that pop up for all of them, as can be detected from these 0 sub-indices. Then here, all the way back at the end, I have a stationary part with the error process eta t, and also in the first equation, the stationary co-integration relations. Now, this second term over here plays the most crucial role in the Stock and Watson representation. Remember that the row dimension of J is n minus h. And so I have here n minus h common stochastic trends. So I originally had n series that are non-stationary. There are h co-integration relations among the series that are stationary. So that means that the series are then jointly driven by n minus h, the difference between the both, of common trends, which are nicely centered out here in this common trend representation. Let's also have a closer look at how we can obtain the Stock and Watson representation for our example. So from the second equation, which is the random walk model for y2t, I can alternatively express it here like this, which we know from the lecture weeks on the random walk model. And that gives me immediately the second equation that I need. To arrive at the first, I then just need to plug in this expression for y2t into the first equation of Philip's triangular representation. So over here, I plug in this expression over here. So note that once you have the Philip's triangular representation, you can actually relatively quickly get the Stock and Watson representation. And then this representation collects all terms with the initial conditions, the common trend, and the stationary part. We nicely see that there is this single common trend popping up. And so since we have two series to start from, that is indeed as expected when we have one cointegration relation. Now we have seen two representations already. So let's have a look also at the final one, namely the error correction representation. Importantly, until now, we only relied on Wald's representation to construct our co-integration representations, Philip's triangular and Stock and Watson. In order to get this third representation, we need to make an additional assumption, namely that yt has a finite VAR representation. So while you can freely move between Philip's and Stock and Watson, you need to rely on an additional assumption, this one over here, for the error correction representation. And so if yt has a finite VAR representation, we can write it like this, where I introduce a new lag polynomial phi L this time for compact notation. Now, what can we say about the co-integration rank and the co-integrating vectors? Well, on the next slide, I'm going to combine these two equations. So let's start from the difference operator applied to the error terms. But now I rewrite my error terms based on the finite VAR representation, the red one from the previous slide. That gives me then the lag polynomial phi L that operates on my series here in differences. And I rewrite my series in differences based on Wald's representation from the previous slide as highlighted in blue to arrive then at this expression. Now, alternatively, making use of z instead of the lag operator L, I obtain that 1 minus z, so z instead of L, needs to be equal to the product of these two lag polynomials over here, because these are the terms in front of epsilon t. And that for all values of z. So it also needs to hold for z equal to 1. And when I plug this in to my expression, I arrive at the expression in the box. Now, what do I conclude from this? Well, remember that we had another expression already where psi1 was popping up, namely this necessary condition for co-integration, where the matrix A prime contains the co-integrating vectors in its row. Now, what do we know from this? Well, let's say that phi is a row of the matrix phi1. Then we know that phi prime times psi1 needs to be equal to 0. But that is exactly the property of a co-integrating vector. So phi needs to be a co-integrating vector. Now, the co-integrating vectors are not unique, but the rows of A prime, A1 up until AH, form a basis of the co-integrating space. So I can write any co-integrating vector, so also this phi, as a linear combination of A1 up until AH. And I can repeat this argument for all the remaining rows in phi1, since each of them is a co-integrating vector. Or in other words, each of them can be written as a linear combination of the co-integrating vectors. And this is exactly what this box says. There needs to be a matrix B such that each row in phi1 can be written as a linear combination of the co-integrating vectors contained as A1 up until AH in the rows of A prime. Now, how to incorporate this into our VAR? Well, just like we did for the ADF test, I'm going to first define here some new notation, where the row matrix is the sum of all of the phi matrices that pop up in the VAR. And these zeta s's, they cut off all matrices as of lag s plus 1, such that I can use the same trick here to rewrite my VAR in levels in terms of the rho and the zeta parametrization instead of the phi's. Now, why am I doing this? Well, I have here this, the identity matrix minus rho popping up, as you saw here on the last line. Have a detailed look at the derivations in this last line. But so you have the identity matrix minus rho popping up, which is nothing more than the identity minus all phi matrices. Or alternatively, this is phi1. And it is exactly this phi1 that I had rewritten in terms of two lower rank matrices, B and A prime, on the previous slide. So this over here was what I obtained in the box 2 slides ago. So if I plug in this now into this expression at the top of the slide, so plug that into the expression at the top of the slide, and I bring my lagged y to the left-hand side, I arrive here at the error correcting representation that expresses my co-integrating system in terms of a set of equations now for the series indifferences. Let us also take a pause over here and inspect this equation. First, I would not have this first term over here. If I would not have this first term, then we would recognize the model equation of a VAR of order p minus 1 for the series indifferences, since we reread the series indifferences just on its lagged values. Now we don't have a VAR indifferences because this term also pops up. And what is this term? Well, A prime times yt minus 1, or our co-integration relation at time point t minus 1. So our short run dynamics, as we would model through VAR indifferences, are corrected towards the long run dynamics through our co-integration relations, hence the name error correcting model. And if matrix B captures the adjustment coefficients of each series in the model, namely how the short run dynamics are corrected or adjusted back towards the long run co-integration relations. Now we will intensively work with this error correction representation next week, and we will crucially see that we can determine the co-integrating rank from the reduced rank of these matrices in front of this guy over here. More on that next week. Now, let us go one more time back to our example. In order to get it into an error correcting format, we need to do some rewriting for the first equation to express the series indifferences in terms of lagged values of the series in levels. Now, we can immediately rewrite it in this format over here, where I just have the first error in differences, and I plug in the difference of y2, since that is equal to the error term epsilon 2. Now let's work conveniently with these initial conditions over here. And then if we again take the sum of both the left and right-hand side from s equal to 1 up until t, we arrive at this expression. Now this line, of course, holds for any time point t, so also for t minus 1. And I'm interested in this equation at time point t minus 1, since my first error term pops up in this equation at time point t minus 1. And I can then plug in my red expression to rewrite the first equation. Okay, so I managed to express the difference of y1 in terms of lagged values of y1 and y2, as they pop up as predictors in the error correcting representation. Okay, so in the last step, I need to plug in my co-integrating vector, as well as the parameter matrix in front of the lagged y's to arrive then at this final expression. Now we've seen today 3 representations, and we illustrated them on one underlying example. In order to really understand how to write a co-integrating system in a certain format, it is a good exercise to dive into these representations yourself to get a better feeling with them. And that is exactly what you will do in your tutorial assignment.